Okay, so we're going to continue on with Chapter 2. This will essentially be lesson number 2 from Chapter 2. So today's topic will essentially be a discussion of the definitions of trigonometric functions. Definitions of trigonometric functions. And so a trigonometric function has as its domain terminal numbers. So inputs into trigonometric functions are terminal numbers. And so from the previous lecture, we have a reasonable understanding of what terminal numbers are. So let me draw a picture. Okay, so 1 second. I'll have the picture stood up for you. All right, so here we have, in the first illustration, the unit circle drawn in the XY plane, centered at the origin, and I show a terminal number, which terminal point is in the second quadrant, denoted as P. So P is the terminal point for terminal number T. All right, and so we have definitions for 6 trig functions, trigonometric functions. So if T is any real number, and P is the terminal point on the unit circle, now the emphasis is the unit circle, we define the trigonometric functions on the unit circle. So the sign, SIN, of the terminal number T is Y. So basically Y is the ordinate of the terminal point. Okay? And so as you may know from previous trig experience, the sine function is written as SIN, and the mathematicians abbreviate it. They drop off the last vowel to make it sine. Okay? And then the next one is the cosine of a terminal number. Okay? And we drop off the last 3 letters for consistency's sake. And so we have the cosine of the terminal number is essentially the abscissa of the terminal point. Right? And now the tangent, we define the tangent written as TAN, okay, tangent. And TAN is the math symbol representation, not to be confused with a tangent line, but the tangent function, okay? All right, so the tangent of the terminal number is the ratio of the ordinate to the abscissa of the terminal point. Or another way of saying this is to say that the tangent of T is equal to the sine of T over the cosine of T. All right, and these are all definitions. Okay. Then we have, we'll go this way. The cotangent of T is the ratio of the abscissa of the terminal point P to the ordinate of the terminal point P. In other words, x over y. So that's a cotangent. So the cotangent T is essentially 1 over the tangent of T. And of course, whenever you do a division, you have to watch out for 0 in the denominator. And that's what those restrictions are. And then we have the next function, we'll call it the secant of T. All right, so we have the secant, written as SECANT of T. And that is the reciprocal of the abscissa of the terminal point, 1 over x. And then CSC is the cosecant of T. and that is 1 over the ordinate of the terminal point. All right, so those are the definitions. You must memorize them. Okay, no way about it for the rest of the class. All right, and I think you guys are okay with that. All right, so now we can build a table of outputs for select values of terminal numbers. So for instance, if our terminal number is 0, t equals 0, then we're right here at this point that I've accentuated in black. And so the coordinates of the terminal point for terminal number t equals 0 are essentially 1, 0. And so the sign of t equals 0 is the ordinate of the terminal point, which is 0. Okay? And the cosine of t equals 0 is the abscissa of the terminal point, which is 1. And so we take the ratio of sine t over cosine t to get the tangent of t equals 0, and so 0 over 1 is 0. Okay? Now, for the cosecant of t, since y is 0, okay, since y is 0, we can't do the division, so the cosecant of t equals 0 is undefined. Okay? The secant of t, which is just 1 over x, which is x being the abscissa of the terminal point, again is 1. And so the cotangent of t equals 0 doesn't exist because, again, x over y being 0. Okay, and so you can follow the rest of the entries in the table. I'll do a few selects. So for instance, how do we know that the tangent of pi 6 is the square root of 3 over 3? Well, you just divide sine of t divided by the cosine of t equals pi over 6, and you'll get the square root of 3 over 3. All right? And we know that these two numbers, 1/2 and the square root of 3 over t, follow from the proof that we did from the previous lecture. Okay, how about the cosecant of t equals pi thirds, this entry? How do we know this is the case? Well, cosecant is 1 over the ordinate of the terminal point for pi thirds, and the terminal point for pi thirds we showed in a proof was square root of 3 over 2, so you take its reciprocal and you get 2 over the square root of 3, and then they did a rationalization and got 2/3 times the square root of 3. So that would be the cosecant of pi thirds. So work through the remaining entries of the table, and it should make sense to you. All right, so we have definitions. That's all it means. Now, as far as the domains of the trigonometric functions go, sine t and cosine t are defined for all real numbers. Okay. Now the tangent function, okay, that's a little bit trickier as far as the domain of the tangent function. So let's talk about that. Now this goes back to our topic from the first lecture where we talked about domains or compositions of functions. So essentially this is what so we know that the tangent t is y over x, and so this originates from a composition, which is sine of t divided by the cosine of t. Okay, so there's your composition. Okay, so x can't be 0 for the tangent function. Okay, so but what is x? X is equal to the cosine of t, which can't be 0. All right, so the question is, where is the cosine of t equal to 0? And that will describe the domain for the tangent function. All right, and so the way we figure that is, okay, we look at points, terminal points on the unit circle, and we try to find out where those terminal points, the coordinates of those terminal points where the abscissa is 0. Okay, and so that would happen where? That would happen at this point, right? What are the coordinates of this terminal point? 0, 1, right? And then it would also happen at this point, at 0, -1, okay? And so what terminal numbers generate a terminal point of 0, 1? Well, if t were equal to pi halves radians, then the coordinates of its terminal point are 0, 1. So clearly, t cannot equal to pi halves, okay? Because cosine of pi halves radians is 0. How about 0, negative 1? What terminal number gives you a terminal point of 0, negative 1? Well, that would be t is equal to 3 pi over 2. Okay? And so t cannot equal to 3 pi over 2. Are those the only two values of t for which tangent of t is not defined? Well, no, it's not, because what if I stood at this point and I made one lap around the circle and came back to the point? In other words, we have this. T, which is equal to pi halves plus 2 pi, okay? Its terminal point is 0, 1. All right, so this is another value of t. Pi halves plus 2 pi is not the same as pi halves, okay? Likewise, I could go clockwise instead of counterclockwise, so I could subtract 2 pi. Okay? Okay, so I could play these kinds of games. And the same holds true with 3 pi over 2. I can add 2 pi to 3 pi over 2 or subtract 2 pi from 3 pi over 2. As a matter of fact, I can add any multiple of 2 pi. Okay, well, 2 pi n. N is an integer. I can add or subtract any multiple of 2 pi to pi halves, and those would be forbidden values for t. Okay, so we can do this. And then I can add or subtract any multiples of 2 pi. Okay, all right. So, but we're still not quite done yet with the domain of the tangent function. We can simplify these two numbers. Okay, now look, if I were to start at this point and I were to go counterclockwise pi radians, I would be at 3 pi over 2. Okay? And if I started at 3 pi over 2 and I go counterclockwise pi radians, I would be back at pi over 2. So we can simplify these restrictions on t to say, okay, I can start at pi over 2, that's an illegal value, and if I were to go pi more, I would be at 3 pi over 2, and that's an illegal value. So, in fact, we can actually strike these 2's and use these values of t. So here's the totality of all of the terminal numbers that you cannot plug into the tangent function. Pi halves plus some integral multiple of pi. Right? And these numbers are called periodic numbers. Okay? So they repeat themselves. These numbers, like for instance, this number repeats itself every 2 pi. So we say that it has a period of 2 pi for this particular terminal number. So by periodicity, these are the terminal numbers. And we'll talk more about periodicity later when we sketch the graph of the function. Okay. Now, the same restrictions would hold true for the secant function because x can't be 0. And so the tangent and the secant functions have the same domain. So in writing the domain, okay, so the domain of tangent function is equal to the domain of the secant function, which is equal to the set t. Sorry, that should be a t. I should write t. Sorry, let me write it again. Domain of tangent of t is equal to the domain of the secant of t, which is equal to the set of real numbers such that t cannot be an integral multiple of pi halves, a pi in multiple. Pi halves, that is pi halves plus an integral multiple of pi, where n is an integer, either positive or negative. Okay, and we'd write this to denote that n is an element of the set of integers. Capital Z means the set of integers. All right, and so how about the restrictions on the cotangent function? Well, the cotangent function is where sine of t cannot be 0, right? So, next page. Okay, so we want to calculate the domain of the cotangent function. Which is the same as the domain of the cosecant function. All right, and so cotangent t, by definition, is the cosine of t divided by the sine of t, and the cosecant of t is 1 over the sine of t. Okay, so the restrictions are, for these two functions, the sine of t cannot be 0. So the ordinate of the terminal point for t cannot be 0. And so where does that happen? On the unit circle. So going back to our diagram, that happens at these points. So at this terminal point, the ordinate is 0, and at this terminal point, the ordinate is 0 on the unit circle. So this is 0, this has terminal number 0, this has terminal number pi. Okay, and if I were to do another lap around the unit circle, I would go 2 pi, so 2 pi has a terminal point of 1, 0, and 3 pi, and so on. So any integral multiple of pi would have a terminal point with ordinate 0. Okay, so therefore, the domain of cotangent t along with cosecant of t is equal to the set t, that's sloppy looking t, that would be the set t such that t cannot be an integral multiple of pi. All right, so that's the domain of this function. So now we have the domains of all the trigonometric functions. Okay, so now how about the signs? Not SINE, but the SIGNs of the trigonometric functions. All right, so let's go back to that illustration of the unit circle. Okay, so let's consider quadrant 1. So this is quadrant 1. Now in quadrant 1, both x and y are positive. Okay, so therefore, in quadrant 1, all of the trigonometric functions, generate positive outputs. Okay, where they're defined. Now consider quadrant 2. Now in quadrant 2, x is less than 0, and y is greater than 0. So in quadrant 2, the sine function is greater than 0. The cosine function is less than 0. The tangent function will have to be less than 0. The cosecant function would be greater than 0. The secant function would be less than 0. And the cotangent function would be less than 0. Okay, so the only positive functions, positive output functions would be sine and cosecant in quadrant 2. The rest yield all negative outputs. Okay, now let's go to quadrant 3, where both the abscissa and ordinates of the terminal points are negative. So here's Q3. All right, so that means sine is negative, cosine would be negative. Okay, the tangent would be positive because we're dividing two negative numbers. The cotangent would be positive. Secant would be negative, cosecant would be negative. All right, and then there's quadrant 4. Okay, so in quadrant 4, the abscissas are all positive and the ordinates are negative. So the sine function is less than 0. The cosine function is greater than 0. The tan function would have to be less than 0. Cotangent would have to be less than 0. Secant would be greater than 0. And the cosecant function would be less than 0 on its outputs. So those are the signs, S-I-G and S, of the trigonometric functions. All right, so now we can calculate the outputs of the trigonometric functions. So in doing so, if you're to do this on your calculator, you'll have to make sure that your calculator is in radian mode and not degree mode to do this. All right, so if you need help with this, get with me and I'll show you how to do that, how to run these calculations on your calculator. So let me pull up an illustration. All right, so to calculate, well, let me show you first before I talk about it. Do some examples. Okay, so in this first example, I want to calculate the cosine of 2 pi thirds, 2 pi over 3, which is shown by this red arc. So 2 pi over 3 has a terminal point in quadrant 2, so we know that the output is going to be less than 0 because the cosine of a terminal number is the abscissa of the terminal point, and in quadrant 2, the abscissas of terminal points are negative. All right, so the way we deal with it is we find the reference number for 2 pi over 3. Okay, so we find the reference number, which happens to be pi thirds. Then we use the results of the table or the from the first lecture, and we know that the cosine of pi over 3 is 1/2. Okay, so since we're in the second quadrant, we would have to negate 1/2 to get the output, which is the abscissa of the terminal point. So that's how we do it. Okay, now, as far as the tangent of pi thirds, okay, to calculate the tangent of, that's the tangent of negative pi thirds. Okay, so where is negative pi thirds? Negative pi thirds would be in the fourth quadrant, right? So it would be somewhere, oh, here it is, it's shown in this figure. Okay, so negative pi thirds is in the fourth quadrant, t equals negative pi thirds. So in this case, the reference number for negative pi thirds, well, the shortest distance from the terminal point here to the x-axis is pi thirds. So we replace negative pi thirds with its reference number, okay, and that is pi thirds. And then we look at our table from the first lecture of this chapter, and we know that, well, we have to do a couple of things. We know that the tangent of t is the sine of t over the cosine of t. All right, so we replace tangent with its definition. and then we evaluate t is equal to pi thirds. Okay, and then so from the table, we know that the sine of t was, at t equals pi thirds, was the square root of 3 over 2. Let's see, make sure that that's correct. Yeah, so we go to that previous table. The sine of pi thirds was the square root of 3 over 2. And then the cosine of pi thirds was 1/2. All right, and so when you do the division, the tangent of this reference number is the square root of 3. All right, now in quadrant 4, okay, since we're dividing a negative number by a positive number for the tangent function, we have to negate the square root of 3 because the tangent function is negative in quadrant 4, as demonstrated previously. Okay, so that's how that works. You basically convert the argument to the trig function to its reference number, and then you make the determination of the sign based on the quadrant in which the terminal number's in, and then piece together your answer. Okay, so now let's go with 19 pi over 4. We're going to calculate the sine of 19 pi over 4. So 19 pi over 4 is almost 5 laps around. It's very close to 20 pi over 4, right? So 20 pi over 4 is 5 pi, and so 5 pi, odd multiples of pi have terminal points at -1, 0. Okay, you should know by now that odd multiples of pi have terminal points at -1, 0. So 19 pi over 4 would be, you go counterclockwise 20 pi over 4, and then you go clockwise back pi over 4 to go back to 19 pi over 4. So this is the terminal point for 19 pi over 4. It's somewhere in the second quadrant. And the reference number for 19 pi over 4 is pi over 4. And so from the table, we know that the sine of pi over 4 is the square root of 2 over 2. Okay? Let's see what else here. So this is the answer. And we know that the sine function is positive in quadrant 2. Right, so that's how that works. And then using this information, of course, you could calculate the cosecant of 19 pi over 4. That would just be 2 over the square root of 2. And we know that the cosine of 19 pi over 4, well, that would just be negative square root of 2 over 2. So I'll leave it to you to verify that the cosine of 19 pi over 4 is equal to the negative of square root of 2 over 2. All right, and you'll use the table for that. Okay, so some examples. All right, okay, so other things about the trigonometric functions is that they have even and odd properties. So recall the lecture from the last class about how we characterized even and odd functions. Okay, so we go to another page, and I'll put up a table for you about the even and odd properties of the trigonometric functions. All right, so let's consider this table, or this illustration right here. See if this will work. All right, so the sign of a negative terminal number. So if we negate the argument to the sine function, negative t, all right, so let's start off by looking at this picture. If t is greater than 0, so here's t, And then the negative t would be the reflection about the x-axis, right? So we know that the sign of a terminal number is the ordinate right here. So if we take t, if we take the terminal point of t to be xy, then the terminal point of negative t would be x negative y, right? And so the sign of negative t is essentially negative y, right? So we have the sign of negative t is equal to negative y, right? But y is simply the sign of t. So it's the negative of the sign of t. Oops, ran out of space there. Which is equal to the negative of the sign of t. Okay, and so recall an odd function has the property that f of negative t for an odd function is the negative of f of the function of the negative of the argument. Okay, which is equal to the negative of f of t. So that's an odd function. So sine is an odd function. All right, so let's consider the cosine function. So the cosine of negative t, okay, so would equal to x. Okay, the cosine of t is, well, oh, let me backtrack. I got my handwriting messed up. Okay, so again, the cosine of t is equal to x. Okay, so the cosine of negative t, all right, based on this illustration, is also x. Okay, so that implies that the cosine function is an even function. Okay, all right, and so if the cosine is an even function, then its reciprocal function, 1 over cosine of t, which is 1 over the secant of t, is also equal to the secant of t. So if since cosine is even, it follows that the secant function is even. And likewise, if the sine is an odd function, then its reciprocal function, the cosecant function, would also have to be odd. All right, now for the now both tan and cotangent are odd functions because an odd function divided by an even function is always odd. Okay, so it just follows readily from that. And you can verify this claim by just checking against this illustration. Okay. All right. And so the next thing is the notion of what are called identities, trigonometric identities. So we'll start. We're going to be doing quite a few of those, and I'll give you a few fundamental ones right now. Trigonometric identities. All right. So it follows like this. We have what are called reciprocal identities. Let me paste that in to the website. Now the reciprocal identities follow just merely from the definitions. Okay, so we know that the cosecant function is the reciprocal of the sine function. The secant function is the reciprocal of the cosine function. The cotangent function is the reciprocal of the tan function. And then here are the definitions of tan and cotangent. All right, so these are called the reciprocal identities, these 5 identities. Now we have what are called the Pythagorean identities. It follows essentially from the fact that, well, the first one, sine squared plus cosine squared is equal to 1. It follows from the fact that we're working on the unit circle, and we know that the sign of a terminal number is y. Okay, So basically, this is y squared, and we know the cosine of a terminal number is x, and we know the equation of our circle is x squared plus y squared is equal to 1. So it follows from this. Now these we have to work at a little bit. So I can show you how those are derived. They come from using the reciprocal identity. So let's show y tan squared t plus 1 is equal to secant squared. So we want to show that tangent squared. And there'll be quite a few WebAssign problems where you'll have to do these kinds of manipulations. Okay, so the way we would demonstrate this is we replace the tangent function with its definition. So the tangent function is, or the tangent squared function is sine squared t divided by cosine squared t. Okay, and we have to add 1 to this, so we replace 1 with cosine squared t divided by cosine squared t. This is 1, so that we can add the 2. All right, and so this is equal to sine squared t plus cosine squared t, all divided by cosine squared t. And then if we add the components of the numerator, well, sine squared plus cosine squared, as we said, is 1, so that's 1 over cosine squared t. And then we know that that's equal to 1 over cosine t, all of that squared. Okay, and we know 1 over cosine t is secant. So we write it as secant, and we put the 2 before the t. So that's secant squared t. So that's 1. Okay, what else? Okay, so 1 plus cotangent squared t. So we have this identity, 1 plus cotangent squared t is equal to cosecant t. Cosecant squared t, excuse me. The proof of this is the same as this proof. So I will leave it to you to demonstrate that. Okay. So we use the, these 3 identities. The last 3 are called the Pythagorean identities. All right, so that is it for the second lesson of Chapter 2. So now in the third lesson of Chapter 2, I'll start it. I may not finish it because I have to have another class to go to or other matters to attend to, but we're basically going to work on graphing the trig functions, the trigonometric functions. Okay, so I'll start, but I'm not sure if I'll finish it. As a matter of fact, what time is it? Yeah, okay. All right, so graphing trigonometric functions, okay? So all you do is you just, the graphs are basically assembled from function tables. You just take some terminal numbers, plug it in, and calculate what the abscissas are and the ordinates are and the ratios, and then you'll have the respective graphs of the trig function. So I can start off with a table, a couple of tables. Let me pull up the note here. So I'm going to build kind of a compressed function table for sine and cosine. And it's going to look like this. Let me paste it into the whiteboard. So as you know now, we have these following results. As t ranges in the first quadrant, so from 0 to pi halves, that's the first quadrant. Okay. Okay. So in the first quadrant, on the unit circle, that is. Okay. Sine of t is essentially the ordinates of all the terminal points. And so, as you can see, as t goes from 0 to pi, increases from 0 to pi, the ordinates of each terminal point ranges from 0 to 1. Okay, it takes on all values between 0 and 1. And the abscisses of the terminal points range from 1 to 0. Okay, so that's easy enough. So we'll account for that in our graphs, which we'll do very shortly. Now, from pi halves to pi, the second quadrant, the ordinates of the terminal points range from 1 here down to 0. And the abscisses of the terminal points range from 0 at this point down to -1. Okay, because that's -1, right? So we have this range. And from pi to 3/2 pi, the ordinates range from 0 here down to -1. And the abscisses range from -1 down to 0, up to 0, excuse me. So we go from -1 to 0 for the abscisses. And then from 3 pi over 2 to 2 pi, the fourth quadrant, the abscisses, the ordinates, which are sine of t, ranges from -1 to 0, and the abscisses range from 0 to 1. So that's basically how you would visualize the outputs of the trig functions, the trigonometric functions. And so we'll translate that into a graph. But before we do so, I want to talk about the periodic properties of the functions. So we have this result. Okay, the sine function has a period of 2 pi. That is, what we're saying is, this formula holds for any terminal number. So the sine of a terminal number will yield the same output as the sine of t plus 2 pi. Okay? And so 2 pi is called the period, and this is called the periodicity of the function. So the output of the value, the output of the sine function repeats itself every 2 pi. Okay? So you pick a terminal number, calculate the sine of that terminal number, then add 2 pi to that terminal number. In other words, do 1 lap around the unit circle, and you'll achieve the same output again. And cosine function also has a period of 2 pi. Okay, so these are periodic properties. Turns out that the secant and cosecant functions also have the same period, since they're simply the reciprocals of the functions. But their graphs are a little more complicated, but they have the same period. The tangent and cotangent functions don't have the same period, so we'll discuss the periodicity of the tan and cotangent at another time. All right, so now I'll show you how to graph the functions. Okay, it's not too difficult. So let me grab the sketch. We'll start off by graphing the output of the sine function. And here it is. Okay, so the way you construct the graph of the sine function is, okay, first of all, consider this figure on the left, the unit circle. And we're going to graph the output of the sine function as for terminal numbers between 0 and pi halves. So here is t equals 0 right here, and t equals to pi halves. So as we know, the sign of any terminal number in this range from t equals 0 to t equals pi halves will be the ordinates of the terminal points. Okay, so what you do is you basically identify each terminal point, and this would be, for instance, the y value. Take this point t0. Okay, so here in this illustration we have a terminal number of t0, t sub 0 or t0, and you see right here is the ordinate of this terminal number. So what you'll do is, for your function at t sub 0, okay, you plot the ordinate for the sine function, right? So you see how this point right here translates to a point here. And so we we'll do this from from t naught equals 0 to t naught equals to pi halves, which happens right here. So at t naught equals to pi halves, the ordinate of the terminal point is 1. So this is 1 right here. Okay? So I think these findings are summarized in the table, which I should paste here as well. So let me grab that table. Yeah, I should have pasted that table. Okay, so consider this table. Just for the sine function. We're doing the sine right now. So at t equals 0, the output of the sine function is 0. So this is your function table right here. At t equals pi 6, the output is a half, which we proved in the first lecture of chapter 2. Pi thirds, the output is, okay, square root of 3 over 2, and you see up to pi halves, it's 1. So that is demonstrated by this this particular arc right here, which I'll accentuate in purple. So right here, from 0 to pi halves, we have this purple arc. So these numbers right here. Okay? And the sine function, since it exists at every terminal number, will be a smooth curve. There will be no sharp corners or discontinuities. Okay? Now, from pi halves to pi, okay? Again, we use our knowledge of the ordinates of the terminal numbers from from pi halves to pi, and we'll get the set of outputs right here. Okay, for t greater than pi halves, and that would translate into this green part right here. Okay, so that range of numbers, and then for t greater than pi, but t less than 3 pi over 2, we know that at t equal to 3 pi over 2, the output is -1. So right here, so this is -1 right there. Y equals -1, and so the sine function ranges from 0 to -1 on this interval. So this would be right here. This would be t is equal to 3 pi over 2 right there. And then finally, we go from 3 pi over 2 back to 2 pi. So our output ranges from -1 to 0 on this interval. Okay, and so you can see that the sine function ranges from -1 to 1. Okay, that is the full range of the sine function. And we have just graphed the sine function over one period. Okay, that's one period of a graph of the sine function. All right, now, because of periodicity, what periodicity means is that we can take this sketch of one period of a sine function and we can paste it at the end of where this piece of the sine function ends. So we can take all of these points, the locus of these points, and paste it right here. So let me show you that in the next illustration. Okay, so next page. We'll kind of summarize the sketch of the sine function in the next figures. Okay, so the first figure summarizes what I just went over. In other words, here they put the granularity, the refinement of the t-axis. They did more values of t in the previous graph, and they demonstrate the outputs of the sine function. And again, this is over one period where t is between 0 and 2 pi. Now, okay, so now talking about what I meant by periodicity. All right, so one period of the sine function is this, what I'm accentuating in blue. This is one period. So if you want to sketch multiple periods of the sine function, okay, say what you do is you go to 2 pi, and then you'll tack on this blue curve to the end of where it ends at 2 pi. So you take all of this blue curve and you basically tack it on. This is called a cookie cutter. You basically make it look like a cookie cutter approach. So we take the blue curve and we just paste it to the end. So the black curve is the same as the blue curve, except it's pasted at the end of the blue curve. And so there's the second period. You can also take this black curve and you can paste it to the beginning. All right? And so you can complete the cycle like that. Okay? So the sine function from this graph, you can tell, is not a one-to-one function, because the reason why it's not one-to-one is because we have many inputs, like 0 pi, 2 pi, and 3 pi. Many inputs map to the same output, which is 0. Okay, so sine function is not one-to-one. Okay, so we can do the same thing with the cosine function. So let's do that next. Let me grab the illustration. It's essentially a circular function table is what it is. That's all it is a circular function table. All right, so here's the cosine function. And so one period of the cosine function is sketched in the first illustration. Okay, and so for each terminal numbers ranging from 0 to 2 pi in increments of pi over 6, we plot the corresponding outputs of the terminal numbers, which would be for cosine, which would be the abscisses of the terminal points. Right, and so one period of the cosine function would be this piece right here from 0 to 2 pi, and then we take the blue piece and we copy it, and then we paste it at the end of the blue curve. And so this would be 2 periods of the cosine function. Okay, because we know that the way we know that, as well as with the sine, we know that the cosine of a terminal number is equal to the cosine of t plus 2 pi. Right? Okay. All right, so I believe that's all I have time for the sketching of the graph. So in the next discussion for graphing trigonometric functions, we're going to be doing vertical shifts, horizontal shifts, vertical stretching, vertical shrinking, horizontal shrinking, and horizontal stretching, just like we did in the first lecture of the class. And so we'll see how we can do that easily. All right, so until next time.